comparably bright to a core collapse supernova, but they leave the star intact and they don't emit neutrinos at all.
Okay, thank you.
Okay, so in the interest of time, this is wonderful. Tomas, were you going to go ahead, Tomas? I'm sorry.
Thanks a lot, John, for the talk in the early morning hours on your time. I don't want to go into details also because of the advanced time. Let me just comment, because I'm co-author on this Fiorillo paper, which you pointed out. I don't agree with the comments you gave. That's of course, but we would have to argue, and I don't want to do this in the audience here. On the other hand, I must say that this statement that this paper was written after US was out is not quite true. The project was a longer term project and it was ongoing already. And there was an incidence that the papers came in a short row. And we actually didn't even want to comment on the one you had written, but we had to somehow include that. Okay, thanks a lot. I heard your arguments and I just wanted to leave the comment that I don't agree with them.
Okay. Okay.
Well, quick comment on that. Thomas likes to talk about this, that he was working on this already with a master's student paper. But if you go back and you read the master's student paper, it actually has nothing like this that we have. Our paper came out, we sent it to you for comments well in advance of putting it on archive. You did not talk about a master's student paper at that time. I went and looked up the master's student paper later. It has nothing relevant to this in it. Your paper came out several months after ours, and it does a very poor job of giving credit to ours.
It was not the same topic. We had a different direction of investigating the data. You concentrated on the first half of a second, and our paper is on the full scene.
Hey.
Fortunately, I cannot hear you.
Yeah. Okay. So, John, I just want to say, thank you. This was magnificent, and for you, the time is obscene. We really appreciate this. I mean, obviously there was a lot of interest. We could probably keep you up till dawn, but I'm going to get in trouble if I let that happen. So,
okay, thanks to everybody. Sorry for you not being there in person. I wanted to be there, but United Airlines didn't want me to be.
Yeah, right. Let's thank John. Okay. Who's chair?
So I'm going to PDF file. Yeah, this one. Yes. So we're gonna start the next session, and we're gonna keep the length of the talks to their nominal length. So we're not gonna shorten the talk. So things will finish just 10-15 minutes later. This one. Okay. Sorry. So this. It cannot go back. Okay, here. This is okay. So first of all, thank you so much for having me this great conference. So I would like to talk about the neutrino quantum kinetic thing, in particular focusing on this self-induced neutrino flavor conversion. So yesterday, Masamichi has already gave a great talk. So today, most of my talk might be a bit overlap with him, but I try to introduce why this topic is very important. So don't get me wrong, so I'm not a Newton physicist. I'm more like a core collapse supernova modelist. So, but the reason why I spend a lot of time to this quantum kinetics is this could be the game-changing ingredient for core collapse supernova theory. So let me get started with this multi-physics element, how messy this supernova theory is. So as we observed, like during this conference, there are many kind of the ingredients like general relativity, numerical relativity thing, MHD thing, neutron transport thing, and the nuclear network, weak interaction. These are microphysics things. Okay, this is a very messy thing. But of course, today, I just only focus on these neutrino transport things. But let me make this problem more messy, okay? So I just use this Thomas figure. So this is really great to see how it's to capture the essential properties of the neutrino transport things in the core crust supernova. So we have the proton-neutron star in the center, around the center of the core, and then around the shock wave. This is not so much high density region. That means in the core crust supernova environment, we have both optically thick and thin regions for the neutrinos. In these optically thick regions, neutrinos and matters are frequently interacting together. That means neutrinos are nearly in equilibrium with matter. We can define the pressure, we can define the temperature. That means hydrodynamics property, like a hydrodynamics treatment is possible even for the neutrinos. But for the opposite limit, optically thin side, neutrinos are just propagated in vacuum, kind of like nothing, no reactions with matters, just propagate straight, okay, along the geodesics. But in the core crust supernova environment, we have optically thick and thin region. That means there is a middle range, semi-transparent region as well. So in this semi-transparent regions, neutrinos are not thermal spectrum. Neutrinos are not isotropic angular distributions. Their angular distributions are actually very complex, and the energy spectrum can be also very complex as well, which is why kinetic framework is very important, okay, kinetic treatment. So we know Boltzmann equation. This Boltzmann equation represents the basic equations for any kinetic theories, not only neutrinos, photons, gas, anything. So, but I would say this is classical neutrino transporting. We just ignore any kind of like quantum things as neutron oscillation, which is the main topic. But I just want to mention here is that, what I want to mention here is that in the core crust supernova modelers, we spend a lot of time to develop such a neutron transporting scheme. So Ryuichiro, the day before yesterday, he gave the talk about recent kind of progress in our Boltzmann radiation hydro simulations in the core crust supernovae. And then this, of course, still keep evolving. And the other groups, like in Oak Ridge, Max Planck, and Lee, so we kind of like try to develop or like a better neutrino transport scheme, which would eventually give some quantitative answer for the quantitative estimation of the neutron signal, for instance, and also core crust supernova explosion mechanism. So, but let me change a little bit gear from the classical to the quantum kinetic things. So as John has already introduced, neutrinos can interact by themselves in the dense neutrino environment. And then these neutrinos propagate in the sea of the neutrinos. They undergo the neutral current kind of reactions themselves. It's essentially the forward scattering. So this is, again, like an analogy of the photons. When the photon propagates in the media, it gains effective mass. Essentially, the same thing happens for neutrinos. Neutrinos can gain the mass because of these self-interactions. So as you know, the essential property of the neutrino oscillation is actually the mass. So when they get the mass, they can actually induce flavor conversion, okay? So which is why this self-interactions is can induce neutrino flavor conversion. The physics is essentially the same as neutrino matter interactions, like MSW effect. But key difference is nonlinear properties in the self-interaction. So again, neutrinos are interacting themselves, and then these interactions can induce some instabilities. Okay, such an instability does not occur in the neutrino matter interaction because this is essentially the linear. But the neutrino-neutron self-interaction, it can induce instabilities. So I just list 4 different instability modes, like associated with the neutrino self-interactions. In the core crop supernovae and also the binary neutron star merger environment, first mode and collisional flavor instability, these 2 modes could play very important role. Let me focus on this topic. 2 mode. So as Ryuichiro introduced the day before yesterday again, so we found that both collisional flavor instabilities and the fast flavor instability can occur in the inner region of the core crop supernovae. This color, okay, this is this blue colored regions and the red colored regions. These correspond to flavor instability region. Okay. So we now know that, okay, flavor instabilities actually occur core crop supernovae. Then what we can do. Okay. And another important thing here is that this model is for the specific Japanese core crop supernova model. But for other models, include Max Planck, Princeton groups, many like supernova models, we see the sign of flavor instabilities. So which is why many supernova modelers now understand this flavor instability should be taken into account for the accurate supernova models. Okay, okay, so how we can incorporate the effects of the flavor instability in the core crop supernova model? The straightforward strategy is we solve quantum kinetic equations for the neutrinos. So please take a look at this equation. It's very similar form as classical Boltzmann equations. So let me go back to this Boltzmann equation. It's essentially the same, right? But what I want to mention here, I'm so sorry. Okay, here. No. Okay, here. So this F in the classical neutron transport, again, Boltzmann equation, this is a distribution function. But in the quantum kinetic equation, this is not a scalar. This is not a distribution function. It's density matrix. This is because we have to treat neutrino mixing. I mean, quantum coherency we should take into account. So we have to expand this from distribution function to the density matrix. This is very important difference. The other difference is this oscillation term. Okay, we put this neutron oscillation Hamiltonian, vacuum, matter, and self-interaction. So as you can see here, these self-interactions, we see the fact this self-interaction can be written in terms of the F, and we also have the F here. This is a nonlinear nature. Okay. No. Okay. So how we can solve this quantum kinetic equation? This is actually a very computational challenge. That's because, for instance, fast flavor instabilities. This flavor instability, like a wavelength of the neutron oscillation, this is sub-centimeter. But we have to cover 1,000 or even like a 10,000 kilometers for the modeling of the core crop supernovae. Oh, 6-dimensional phase space, such a very resolving such a short spatial scale, it's apparently intractable. We have to do some approximation. So we recently kind of proposed, so if you're interested in, so please take a look at our paper, but we just proposed kind of like efficient approach to overcome this issue. This is just attenuating the Hamiltonian. So we introduce this exercise, this kind of artificially attenuated neutrino self-interaction like a neutrino Hamiltonians. Of course, this is not physical, right? This is artificial. But the key thing here is that neutrino self-interaction, again, fast probability is too short, happening in too short scale. If we just change in the spatial scale from the sub-centimeter to the 1 meter, for instance, of course, this is a kind of artificial one, but global properties are not so much changed. Time average properties, spatial average properties in the scale of, for instance, 100 meter, nothing changed. So which is why this sort of like attenuation prescription can provide some physically meaning quantity, neutrino signal, for instance, and how this can change the supernova physics, okay, explosion mechanisms, etc. This is one possible strategy. How do we resolve? How we can study effect of the flavor instabilities to core-crab supernovae. The second approach is a subgrid model. So again, this flavor instability occurs at a very narrow, very short spatial scale. So we just ignore such a small scale variation. Just again, we can focus on some sort of spatial average quantities. So we can just replace some sort of this Hamiltonian term as relaxation time approximation. So if we know the time scale of this relaxation, and if we know the asymptotic state of the flavor instabilities, yeah, we can just put such term. Okay, we can just replace. And then there are no small scale structures when we solve this one. Okay, so what you're looking at here in the bottom panels, I just compare between direct QK simulations and BGK subgrid model. As you can see here, small scale structures, we see a lot of differences, but some kind of spatial average trend, yeah, actually BGK can capture these trends. So which is why this BGK method, I think, it's very good. And the day before yesterday, Ryuichiro introduced our recent supernova simulations, which actually takes into account effect of the flavor conversion by BGK prescription. Okay. Oh, I just go back. Okay. Okay, let me just again change a little bit gear. So I just want to explain the current status of this field. The terms are actually, I try to answer the previous question, like maybe this, I don't. Okay, so anyway, so I just explained these 5 items. So flavor conversion actually gives the impact on these shock dynamics, neutron signal, proton neutron occurring, explosive nucleosynthesis, neutron static. It looks like everything. But I just try to explain what is the current status here. So first of all, this is the shock dynamics. So what you're looking at here is the simulation from the Max Planck group in the top and the Princeton's group bottoms. So this black solid line shows the result without flavor conversion, okay, here. But the other colored lines represent the result with flavor instabilities, flavor conversion. As you can see here, okay, shock dynamics is actually changed by flavor instabilities. So this Princeton group, this also shows the kind of the sensitivity of the shock dynamics to the flavor conversion. And then this solid line corresponds to the result with flavor conversion. And this is not without no flavor conversion case. And some explodability can be actually impacted. Okay. So the reason here is that neutrino cooling and heating efficiencies are actually changed by the Flavor instabilities. So in these regions, neutrino coolings are dominant. Again, like a black solid line shows the without Flavor convergence, and these colored lines correspond to the result with Flavor instabilities. You can see large dip. So this means neutrino coolings are accelerated. So in the neutrino heating region, I mean gain region, it's reduced, okay, by the Flavor instabilities, neutrino Flavor instability thing. So this actually, okay, I cannot say that whether Flavor conversion can push the shock wave or recede, I mean, play negative role on the shock revival. I cannot say now, but at least we can say shock dynamics would be changed. Okay, this is one important message. Okay, so Flavor conversion can both facilitate and maybe like hinder the shock revival. Okay, next topic is the neutrino signal. So of course the neutrino signals are changed. So and as Masamichi yesterday like I mentioned that this kind of fast Flavor instabilities does not actually reach the Flavor equipartition, strictly speaking. But crudely speaking, it's essentially nearly Flavor equipartition actually reached. Okay, so then these kind of neutrino signals can be significantly different from without fast Flavor instabilities. Okay? So I think this is also very important message for the neutrino detection people as well. Okay, so then the proton neutron star cooling thing. I think there are so many gravitational wave detector guys here. So I just want to focus on how this actually gives the impact on the gravitational wave emission here. Okay, please take a look at the left panels. This is not a result from the core-crop supernovae simulations. This is actually the binary neutron star merger simulation. So this is a Penn State group. They carried out the numerical relativity simulation thing. And what they found is that they compared the simulation result with and without Flavor instabilities. And what they found is that neutron star cooling, in their case, hypermassive neutron star cooling, they are actually accelerated by Flavor conversion. And then, as a result, hypermassive neutron star become more compact. As a result, binding energy become more deep, higher. As a result, gravitational waves signals are actually changed. And this right panels, this is for the core-crop supernova simulation. This is done by the Max Planck group. So this also shows a very interesting possibility how Flavor conversion changed the gravitational wave signal. So they propose that if Flavor conversion occurs very in a region of the proton neutron star, nu x and nu e, it's kind of the chaperone. And then this actually enhances neutrino cooling in the envelope of the proton neutron star. We have the sharp rise of the entropy and then decrease. That means entropy gradient becomes a negative, which facilitates the proton neutron star convection. As you know, if we have a lot of proton neutron star convection, we can have gravitational wave. So this is actually potential impact on the gravitational wave. Okay. So proton neutron star cooling, yeah, likely Flavor conversion likely accelerate the cooling and then give the impact on the gravitational wave. Okay. The next one is the nucleosynthesis. I think Chris asked Masamichi yesterday, so let me just comment on that. Okay, first of all, I just want to mention this is not self-consistent one. What we did is post-processing analysis, given just a light bulb neutrino kind of model, and then just try to explore the supernova by hand. And then we just compare the nucleosynthesis with without Flavor conversion. And this is sort of like a Y kind of ejector properties. So the top panel shows the without Flavor conversion, and then bottoms one that's some sort of like a Flavor conversion things. So neutron survival probabilities are just treated in the parametric manner. Again, this is not self-consistent, but we would like to know what potential impact on that. Okay, essentially, lighter element has insensitive to the flavor conversion. Okay, in particular, like a cobalt, and then on the other hand, heavier than the cobalt, we see some sort of like a sensitivity. So that's because low kind of YE environment, like an ejector, this can be actually sensitive to the flavor conversion. That actually affect this sort of the heavier element nucleosynthesis. Okay. Okay, so heavier elements than the cobalt can be changed by the flavor conversion. And the final one is the neutron star kick. Okay, here's the interesting possibility. So as you know, like a quark supernova environment, it's strongly inhomogeneous, and we have the dipole kind of distributions in the around the proton neutron star surface, low YE environment and high YE environment, something like that. So because the fast flavor instability easily take place around the low YE environment, that means flavor conversion occur asymmetric, anisotropic one. So if we have a fast flavor instability around the southern region, we have a lot of neutrino cooling, as I have mentioned. Neutrinos can carry linear momentum as well. So that means proton neutrons get a recoil. This can actually accelerate the proton neutron star. So I think this could affect the proton neutron star kick, and then maybe like such a kick could contribute to low frequency gravitational wave things as well. Maybe. Okay. Okay, neutron star kick, asymmetric neutron flavor conversion can accelerate the neutron star kick. Okay. Okay, then finally, I just briefly mentioned about how we can constrain neutrino oscillation model. So again, I think quantum kinetics of the neutrino could be the greatest uncertainties in the current quark supernova theory. Of course, we want to place a constraint somehow, but how? I think gravitational wave and the neutrino, this joint analysis could actually contribute this one. Let me just explain the essential thing. So gravitational wave data, if we know total emitted gravitational wave energy, even like upper limit, that's still okay from the galactic quark supernova, for instance. This could tell us the proton neutron star mass. So I and Bartania, we just carefully study this kind of correlation between the proton neutron star mass and gravitational wave energy. It has strong correlation. Okay. This proton neutron star mass also has a strong correlation to the flavor integrated neutrino emissions. So gravitational wave data can tell us neutrinos one through this proton neutron star mass. And each neutrino data, like for instance, the super Camille candle, it is sensitive to the nu E bar. But this detection number is sensitive to the neutrino oscillation model. We know the flavor integrated one, so just comparing to these data, we can place a constraint of the survival probability of the neutrinos and then kind of neutrino oscillation model. This is some kind of like a strategy, how we can use both neutrinos and the gravitational wave. Okay, so this is a sort of like a summary part for the constraint thing, but my time almost ran out. So let me just summarize today's talk. So I think neutron self interactions that could be very important for the quark supernovae. But I just explained the current status, but still it's apparently incomplete. We need to push forward more. But our kind of future should be bright. So because we now developed a subgrid model, we start to incorporate the effects of the flavor conversion in the quark supernova kind of multidimensional simulations, so we can tell more quantitative in the near future. That's it. Thanks for your attention.
Wonderful talk. We have time for a couple of questions. I think we have Coulter here.
Thank you, Hiroki. As always, it's great to hear you talk about this. In your expert opinion on the neutrino flavor oscillations, let's say you have unlimited funding to run your simulations. You can run 6 species, full oscillations. In that scenario where you're evaluating for the entire star, energies might be favorable to get some muon production. And with this mixing, you're talking about the cooling and the gain region being altered. If we mix electron flavor neutrinos into muon flavor neutrinos and can account for that, do you think that would still have a similar effect on the dynamics? Do you think it might make it more favorable for explosion, or do you still think we're in this weird, we're not sure region?
Yeah, nice question. So, okay, here's the thing. The way I see it, so as you know, like heavy leptonic neutrinos, if like no muons, but anyway, so essentially like electron type neutrinos are always dominate over heavy leptonic neutrinos. So then if flavor conversion happens, electron type neutrinos are going down and then heavy leptonic neutrinos going up. So when we focus on the, when we see the opacity thing, because heavy leptonic neutrinos only has a neutral current. So that means the opacity is lower than the electron type neutrinos. That means electron type neutrinos convert to the heavy leptonic neutrinos lower opacity region, which is why neutrino coolings are accelerated. This qualitative trend could not be so much changed even with muons. So because the muon numbers are still not so much. Of course, the charge current becomes open, but it could be still not minor. This is the way I see it, yeah.
Okay, one more. Yes, Tony.
Yep.
Can you comment on the efficacy, the benefit of using the moment approach versus both approach? Talked about some very nice ideas, innovation, things like that.
Yeah.
That's what multi-angle.
Yes.
But obviously, you know, there was hope that, or there still is hope that we might be able to capture this through moments approaches and produce dimensionality. I'd love to get your take on it.
Yeah. So actually, like in the University of Tennessee and many groups, like they, of course, start to develop. They have already developed a moment scheme for the quantum kinetics transport as well. So the way I see it, this is good approximation, but of course the problem is something like a quantum kinetic closure thing. So again, so fast flavor instabilities, this is actually sensitive to the neutrino angular distribution, so we need a multi-angle treatment. But on the other hand, collisional flavor instability, this is another type of the flavor instability. This is sort of very sensitive to only the zeroth angular moment. That means two-moment method is very powerful. So I think one of the another way to include the effect of the flavor conversion into the neutrino transport in the quark supernova theory. Of course, the moment method is good, but again, we need to carefully compare between the two. Again, like first of all, maybe we can just give some qualitative trend by moment method, and then try to quantify more. This is a good strategy and how we can collaborate. Yeah.
Thank you.
Okay.
So in the sake of time, I think we should move to the next presentation.